And so the topic of the talk is on this question of understanding the role of climate change in extreme weather events. Events like storms in Lahinch a few years ago. I was giving a talk in Dublin not long after this event, and I made the mistake. I was reporting our initial results on this storm, and I made the mistake of characterizing the role of human influence in this storm as subtle. And a lady in the audience stood up afterwards, during the Q&A, and said, "My cousin lives in Lahinch. There was nothing subtle about that storm." And so if you're watching online, but no, she was quite right. There was nothing subtle about the storm. It did a lot of damage. But what, of course, I was talking about was the signature of human influence on climate in the storm. And I will try and defend to you this evening that I was right to call it subtle, even though absolutely there was nothing subtle about the storm itself. I like this photograph. My mother's from County Mayo, and I like this photograph because this was the situation after the storm, and it illustrates the historical context of these events. That's a Victorian vintage seawall in the front, which this storm was clearly the first event this storm season, the 2014 storm season, was the first season that actually overcame the infrastructure which the Victorians had put in. But you can see a rather older piece of infrastructure in the background, which was absolutely fine. Of course, the castle in the background was built to withstand Vikings and things as well, so maybe not just the weather, but you can see that there's, it puts these things into context. This was, and in fact, when we looked at the statistics, around a 1 in 100 year season was sort of seemed to be more or less what it was coming out to. But of course, you don't need me to show you photographs of County Mayo. Here's much closer to home, your own floods in 2009, and I think we are somewhere down in the lower left corner of this photograph, and that was the situation which I'm sure many Cork residents remember, the situation in the city centre. And we'll come back to that event. That's actually one of the events that we're going to be looking at in the course of this project, to try and work out what was the role of human influence on climate in the meteorological precursors of that event. But of course, that's only part of the story, and as I'm sure you all know, there's plenty of other factors that translate anomalous meteorology into an actual disaster, and we'll talk about that as well in the course of the lecture. But when these things happen, people like Kieran and I get phoned up by journalists expecting immediate answers on what's the role of climate change in events like this. It became particularly topical in early 2014, because our Prime Minister, then Prime Minister, popped up in Parliament and said he suspected climate change was something to do with these floods without actually apparently having consulted anybody beforehand. And that, of course, meant that lots of journalists wanted to poke microphones at us and ask us to say the Prime Minister was wrong or the Prime Minister was right. And it kicked off quite an intensive amount of research which we undertook to that 2013-14 winter. And in this lecture, I'm sort of going to describe to you a little bit about how that research works and the kind of methods which we're now going to be applying to weather events in Ireland and some of the initial results we've found. To start with, I think one of the sort of big developments in the past year or so on the science of event attribution is it's sort of coming of age in the sense that the national academies are accepting this is a legitimate area of research. That may sound a little bureaucratic or something, if you like, but for a long time, the scientific community was kind of divided on whether you could do this at all. And so we're now getting to the point where, as the US National Academies put it in their report last year, it is possible to make and defend quantitative statements about the extent of human-induced climate change in individual weather events. And I'm pleased to say as well, we've made quite a lot of progress in communicating this to the media and the public in that 10 years ago, whenever a weather event happened, you typically had, the reporting was, yeah, this is weather, not climate, don't be silly, you can't make a link between climate change and individual weather events, and then the conversation was kind of shut down. Then we kind of went through a period where absolutely every weather event was blamed on climate change, which is equally ridiculous. And we're sort of, I'm hoping, coming out of this flip-flop into a period where people understand, yes, climate change is playing a role in the weather we're seeing, but frequently it's not the dominant role, but it's a contributor to the event. And that's the kind of research we're undertaking in this project. So, you know, this lecture is about how we go about answering this question, how we frame the question, what we mean by the role of climate change in a weather event. And first of all, we have to ask ourselves the first question we have to ask ourselves is, how do we quantify the role of human influence on climate, on global climate as a whole? So this is not particularly talking about weather, but talking about the extent of human influence in global climate, and how do we know how much of observed global scale climate change is attributable to human influence? And then, having got that information, how do we translate that knowledge into about global changes into impacts on extreme weather? I cut my teeth in this area, if you like, on the global change attribution question. The question of, you know, most of the warming over the past 50 years is attributable to human influence, or likely attributable, very likely attributable. These kind of statements we argue over interminably in these intergovernmental assessments, and I think everybody else, after a while, gets a little bored and bemused as to why we're interested, and actually the scientific community itself gets a little bored with that kind of question, because that issue was largely answered a decade or more ago. But nevertheless, it's important to understand how it's done, and in particular, in the context of the sort of rapid variations we see in global temperatures due to the weather, and due to essentially weather events, like large-scale weather events like El Nino. You can see here a breakdown of observed global temperatures. And the black line is what actually happened as global temperatures evolved over the past century. The orange line shows a best estimate of the contribution of human factors, combination of greenhouse gas increase and other forms of atmospheric pollution, to that change in global temperatures. And the blue line shows the contribution of external natural factors. So these are things that are external to the climate system. Volcanoes, fluctuations in the power output of the sun are the two key drivers there. And they've also played a role in causing occasional temporary cooling, but the bulk of the warming that you've seen over the past century is due to the anthropogenic influence. The way we estimate these contributions is simply by asking, exactly as an epidemiologist would, how much of when you're trying to sort of tease out in a population what the contribution into deaths in that population is from smoking versus contribution from air pollution or whatever, they use a regression model. That's a typical tool used, and they try and explain the data they have as a combination of various factors. And that's exactly what's done here. We've got a contribution from human influence in the orange line, and we've got the contribution from natural influences in the blue line, and we try and explain the data with these two. And it's all the only technique that's being used here is a linear regression, for those who are familiar with these things in the audience, or it's just you're fitting the data to these two hypothetical drivers, and that gives you a contribution from human influence, contribution from natural factors, and crucially, you don't have to assume how big the human influence is to start with. You're actually estimating it from the data, just as the epidemiologist doesn't assume how much smoking contributes to the risk of death in a population before they estimate that from the actual death data they've got on that population. So these are not, people often, there's a lot of discussion often in the popular press about whether climate models match the observations well or badly. Typically, as the scientific community doesn't really care, because we know there's all sorts of reasons why the climate models might be wrong. We don't really care whether the climate models match the observations exactly. What we do is ask, can we explain the observations without human influence? Is there any way of explaining what's occurred without allowing for the fact that rising greenhouse gases have caused a large fraction of the warming that's happened over the past century? And the answer is we can't. There's no, the data is would be extremely improbable without it, is the sort of negative way you have to frame these things when you're when you're performing a statistical test. So that's what we do, and that's how we estimate the contribution of human influence to global temperatures. And as you can see, the orange line has just sort of reached 1 degree here. It's important that we do this. Partly, this figure really illustrates why it's important to understand the distinction between observed temperatures and the contribution of human influence to those observed temperatures. So I've just highlighted, this is partly for fun, but I've highlighted here the timing of major conferences on climate. And many of you may remember the 2009 conference was a disaster, and the 2015 one in Paris was a roaring success. And you've only got to look at this and think, are we being perhaps a little bit too much at the whim of the weather in making decisions on climate change? And okay, maybe not, maybe the governments are more sensible than that, but certainly the reporting on climate in the build-up to these conferences is certainly affected by just, what's happened last month. And that's why I feel, we had earlier this year, we had headlines, this is from Scientific American, perfectly reputable journal, talking about the Earth flirting with 1.5 degrees, almost at 1.5. And then at the opposite end of the scale, we've got, the Mail on Sunday getting very excited about, where are we? You said that they were very excited about this drop in global temperatures, and so they were highlighting that. But you can also see the drop in global temperatures at the end of this series here, and they were saying this is evidence of global cooling, this huge 1 degree drop. So in both cases, we'd have avoided both of those headlines if we'd have been emphasizing to people not only the temperature that was observed over the past year, but the contribution to it from human influence. And that's something which I'm really pressing the Met Services of the world, the WMO and people, they should do that. It's not enough just to tell people this is what the temperature was last year. You've got to tell them what the contribution is, because it's not complicated to work out that additional attribution step. And it gives you the orange diamonds here show you what you would have estimated the human-induced warming to have been at the end of every year over the past 30 years or so. And if we'd have been showing people that figure, and every time we had a cold year, or sort of a period where years were a little bit colder than the human-induced warming, or above it, we just told them, yes, okay, this is what observed temperatures were doing, but that's what the contribution from human influence is doing. It would have just, I think, made the conversation a little bit easier and more predictable, and perhaps sort of smoothed out a bit of the volatility in opinion on this sort of thing. I don't know. It's perhaps naive, but it's a hope that if we can get people to understand this distinction, it'll make the conversation about climate change rather easier. Anyway, so what has this all got to do with the weather? So where we are now is we're at 1 degree above pre-industrial, give or take, but one's a nice round number, so you can think of it in those terms. I mentioned the preoccupation with climate models. The average warming over the decade we're in the current generation of climate models is 1.2 degrees. So yes, I would say, others do argue about this, about whether this is a significant discrepancy, but I'm quite happy to say, yeah, I think some of the models are too warm. But does that change the fact that we are now at 1 degree? No, it just means some of our models are slightly too warm. So the actual amount of warming we estimate due to past human influence is not dependent on how much the individual models actually warm up. And so we've got this global warming that's happened, and the next question is, okay, does this mean that climate change, and some people take this, okay, that means the climate has changed, therefore whenever a weather event occurs, climate change has played a role in that event. And there's a sense in which that's true. Of course, the weather would be different without climate change, so therefore whenever a storm occurs, climate change has inevitably played some role in that storm. But we have to understand that the role climate change plays, and it's not, you can't say just because the climate has changed you can blame climate for every weather event that occurs. So to explain this, I'm going to use a much simpler model. This is an idealized weather model, which many of you may have come across. It's Lorentz's 1963 model, which orbits around the butterfly. It looks like a sort of slightly skew-whiff butterfly, and you can imagine this point sort of orbiting around and then flipping over here and orbiting around in that direction. It looks, if I showed you this weather model evolving in time, it would sort of evolve in that direction, and then it would flip over and evolve in this direction, and then it might flip over and go there. So you've seen that kind of thing in little pictures. And so this would be a vertical slice. This would be the sort of Z direction here, and that's X. So now we're just going to turn this over, and none of the animations worked, which is why I had to take them all out. So this is more reliable than PowerPoint. Okay, so now we're going to turn this over. I'm going to, you've got to work with me, use your imagination. It's like theatre, isn't it? And so now it's doing this, orbiting around that, and flipping over and orbiting around here, and then we're generating that blue, those blue dots. And then in this, on this system, we now introduce a new element, which, if you like, is sort of like greenhouse gases, like a forcing. And we blow in this direction on the butterfly. Okay, so we've got this little point moving around, and now we put a little steady wind blowing on it, and we ask ourselves how it responds. And the first thing we find, if this is the system going normally, okay. That's the normal system. And now, when I introduce this forcing, okay, it responds like this. So, green's not very good. I'll try and use black, so you can see that. Okay, so it's okay. So what's changed? There's something. Shall I keep going? What I'm trying to do, and it would have been marvellous if only the animation. No. What I'm trying to convey is that I'm spending more time down here, yeah, and that's the sort of what happens when you apply this forcing. You make it hang about down here a bit more than it hangs about up here. But it doesn't go anywhere that it hasn't been before. It just spends a bit more time hanging about down here. So it's not as if we see weather that we simply wouldn't have seen without climate change. And that's the fallacy that a lot of people think. So we wouldn't have seen this weather event without, and then somebody else pops up and says, yeah, wait a minute, I found some medieval record that says we had a drought like this in 1306, and therefore, climate change is bunkum, and so the argument goes on, and what is actually happening is we're not seeing weather that would have been impossible without climate change. We're seeing this shift in the probabilities. We're seeing the thing being, and I was trying not to make it too obvious when I was drawing this, because it isn't that obvious in the real world either. We're seeing relatively subtle, apologies to the woman with the cousin in Lahinch, it's a relatively subtle shift in the probabilities that we're seeing typically in the kind of weather events we're looking at. So that's what happens in the big picture. But if we now zoom in on, this is in an idealized, again, in this idealized climate model, we now zoom in on, so this is, you now know all about how the system works. So I'm now showing you in detail, and this slide, by some miracle, did actually come out. So you can now see that the blue dots are before climate change and the red dots are after climate change in this idealized system. And you can, I hope, see there are more blue dots than red dots here. I should remember not to move around. Sorry about that. So that's this system shifting off down to the other lobe of the attractor here. But the other thing you'll notice, so there's another experiment we've done with this idealized system, which is we've taken a bunch of red trajectories, that's sort of today's climate with climate change present, and then we've taken from exactly the same starting conditions, we've suddenly taken away the influence of climate change and asked how would those trajectories have been different? Yeah? So you can see how this experiment. So you can see what happens is the first thing they do is they jump backwards, because you've taken away this, you're pushing something, you're holding it, and then you take away that push and suddenly they jump in that direction. Fine. And then they evolve forwards in time. Notice where they get to. They don't get as far to the right as the red lines. So what this tells you is, in this system, if you look at an individual event, you'd say that climate change was actually making that event stronger. Yeah, the red lines move further to the right. If you think of, flood damage as going off in the right, yeah? So climate change is making the event stronger, making it worse. And yet, if we look at the system as a whole, climate change is making that event less likely to occur. Yeah? So a few people are nodding. I'm hoping you kind of get the point. It's an example, it seems a little bit mystifying. What I'm just trying to convey to you is just because, for example, a warmer atmosphere holds more moisture and can generate stronger storms, it doesn't necessarily mean that it's making stronger storms more likely. And in a non-linear chaotic system, which is what we're dealing with, of course, in the atmosphere, I'm certainly dealing with it here, just because something is being pushed in one direction doesn't necessarily mean it'll go there. It could sort of jump sideways. And that's what's happening in this simple system. And it shows that it could happen in a chaotic system like the atmosphere. And therefore we can't just say, because the atmosphere is warmer, because it can hold more moisture, therefore you can blame climate change and that warming for every storm that happens, which, you quite often hear that line being played out. That can be misleading. So it doesn't mean it is always misleading, but it can be misleading. And you have to actually do the analysis and work out, is the driving I'm putting onto this system actually making this event more likely to occur or not? And that's the way we have to think about the weather attribution problem. Anybody want further clarification of this? Or would you like me rapidly to move on and stop talking about chaotic systems and get back to the weather? Yes? Oh, sorry, actually, you're going to have to use a mic to... I'll repeat your question just to keep us moving. Oh, there is a mic there. Well done. Thank you.
Can I just ask, you said that we can't predict an increased probability of extreme storm events because of the chaotic period, but could you say that the storm events that do occur would be more extreme because of warmer atmospheres?
No, we can quantify how much the probability of extreme events have changed. So that we can do, and that's exactly what I'm going to be talking about here. So we can talk about how probabilities have changed, but the point here is just to explain that the direction of change of probability may not be the same as the direction of change in an individual event. So the same forcing could make one event bigger, but actually make that same event less likely to happen. And then you've got to ask yourself, well, in that situation, what does it mean to blame the driving for the event that happens. You know, because it made it a bit bigger, but at the same time, it made the overall event less likely to occur. In that situation, you know, if you'd say, well, you know, the climate change made the winds we experienced in this storm, you know, 5% stronger, but at the same time made the entire storm there was only half the chance of it happening. So you'd only get, you know, 5 storms where you got 10 storms before. It'd be quite difficult then to argue that climate change is to blame for the damage caused by the storm. That's what I'm driving at here. That you've got to ask yourself about the changing probabilities, as well as asking yourself about the role of climate change in the individual event itself, if you're going to get a coherent answer to what climate change is doing. Because of course, in the end, people don't really care about exactly how climate change may have affected the meteorology in the run-up to a particular weather disaster. They want to know, was climate change responsible for flooding my kitchen, and am I going to get flooded lots more in the future because of climate change? These are the kind of practical questions people have. They don't really care about the details of the mechanism. They want to know, is this kind of event becoming more frequent because of climate change, and if so, what can we do about the changing frequencies in the future? Did that help? Thank you. So, there's the punchline. Climate change is warming the atmosphere. The atmosphere holds more moisture. We've got accurate records of the moisture content of the atmosphere over the past 30 years. We can see that the moisture loading of the atmosphere is going up. So the energy available for storms is higher. So you could argue, whenever you take an individual storm, that climate change has made that storm just a little bit stronger. But this is really, it's not necessarily loading the dice towards stronger storms. And this is the way I like to think about this kind of problem. If you look at this set of dice here, you see that there's, I hope, far too many, you'll see immediately, I hope, there's far too many 6s. That's exactly the, you can work out, if you want to, as an exercise, the probability of seeing this many 6s. But the point is, if I just took one of those dice just look, if I rolled this dice once and I got a 6, I wouldn't be able to draw any conclusions from that. I have to see it rolled lots and lots of times in order to be able to see the fact that it's been loaded. And when the loading is subtle, this is quite a heavy duty loading, what you're seeing here. So it's obvious, even with a dozen rolls, that this is a heavily loaded dice. But if the loading is only increasing the odds on a 6 by 20-30%, for example, which is the kind of loading we're talking about for many weather events, you need many more rolls of the dice in order to be able to see that. So this is where we use, now to come back to the weather, sort of leaving the analogies, we can think about a sort of 4-sided weather dice for North Atlantic winters, thinking back to that stormy winter a couple of years ago, that example here. These are the sort of 4 sides of the dice. You've got, the weather could sit in this cold northerly regime, a wet westerly regime, this cold, very cold easterly, and a nice warm southerly regime. If you think about, the North Atlantic does these plots here, by the way, are produced by colleagues in France who actually do this kind of cluster analysis, and they can show how North Atlantic weather sort of jumps between these. So it is a little bit like a dice. It doesn't land on a corner. It likes to jump into one or other of these 4 regimes. Okay, so and the question is, so when a weather event happens, it's not that it couldn't have happened without, each of these regimes happens anyway and will continue to happen under climate change, but the question we have to ask ourselves, are we seeing too many of one regime and fewer of another? So the only way we can do this is by rolling the weather dice many times, which is something we can't do just by looking at the observations. Actually, as part of this project we're doing with UCC, there will be an effort to go back over the record to characterize a longer record of extreme weather events, But, and Kieran and a student will be working on that, but one of the problems we have is that even if you go back over a century or more, you still don't see very many 1 in 20 year events. And so, you can't really quantify just by looking at the record what's happening to the risk of these low probability events that really do damage. So we have to simulate them. We use computer simulation to do this, and this is just an illustration of the kind of comparison between observed temperatures, observed precipitation and pressure in the January 2014 winter, and one of the wetter members of our ensemble, so showing that the weather model we're using, which is an adapted version of the UK Met Office weather model, is doing a reasonable job of simulating the kind of conditions we saw that winter. We take this, so we've got this computer simulated dice that we can roll many times, and as Paul mentioned at the beginning, we actually use a global laboratory to do this. These are our participants around the world who we distribute copies of this model to. Everybody gets their own little weather model, which they use to, and in fact, if you want to join in, go to the climateprediction.net website, which I forgot to write on this slide. That was a mistake. But climateprediction.net, it's one word. You can go there, you can download our weather model, and you can be, and is anybody here running it, by the way? Have we got, no? Yeah, thank you very much for, okay. Oh, great, yes, thank you. And so you can help us do these simulations, because one of the challenges we have is, we need to access thousands and thousands of runs in order to see changing risks of extreme weather events. And to do that with a supercomputer would not only be very expensive, it would also be very environmentally unfriendly, because you need to build a hangar and you need to build air conditioning for your supercomputer and all the rest of it. And actually, a lot of people have a lot of computing power sitting in their bedrooms or used for surfing the web or whatever. And I'm sure many of you in this room have much more practical uses to put your computers to, but for the idle time, you can use it to help us simulate the weather. And we very much appreciate the input people make. So here's how we analyze our experiments. So participant A in Cork, for example, got 300 millimeters of rain in their simulated January 2014. And we distributed 10,000 simulations with the drivers, greenhouse gas concentrations, temperatures and so on, sea surface temperatures, set to be today's conditions or conditions in January 2014. And so that's odds of 1 in 200. So now we distribute another set of 10,000. And participant B, and then this set have been modified to mimic a world without past human influence on climate. So we have lower levels of greenhouse gases in the atmosphere, somewhat cooler, slightly cooler sea surface temperatures, and we use a range of estimates of the change in sea surface temperatures to allow for uncertainty in that cooling. And so participant B also got 300 millimeters, which is more or less the threshold of what happened in the real world. But they found that they were 33rd out of 10,000. So in other words, in the natural world, they were a little bit closer to the leader. They were a little bit further up the leaderboard, meaning this event was slightly less likely to happen in the natural world compared to the world as it is. And this tells us that the odds of rainfall exceeding 300 millimeters have increased by 50%. Yeah, you can trust me, or okay, or you can probably work it out from the numbers in front of you. Well, I hope you can, because I did this on the plane, but I think I got those numbers right. Okay, so here we are. Here's an example. This is how it's done. And there's participant A, there's participant B, and these are the actual results from the experiment, as opposed to just sort of numbers I was making up to explain the point. And what we found was a 40% increase in risk in the January mean precipitation in 2014 being as high as it was. So each of these dots corresponds to somebody out there in the world has done a simulation for us, seen how much rain they got, and sent it back to our servers. And all we do is we just plot the dots in order, we rank them, see who got the most rain, who got the least, we put them in order, and then ask, are we seeing a shift in where people are in the rank order if they get a certain amount of rain in these two so-called ensembles of simulation. An ensemble is the way we characterize a whole lot of runs which are similar, but which allow for this chaotic variability in the atmosphere between them. And this is the corresponding result for West Island wind speed. And you can see the same thing. Sorry, I should have explained on this. Red here is the actual conditions. Blue is the various estimates we have of what the world would have been like without human influence. So you can see there's a lot of uncertainty in that. There's some chance that human influence really hasn't done very much at all. You see there are some blue lines here up close to the red line. But the best estimate is that human influence has increased that risk by around 40%. When we look at the West Island wind speed case, again, this is just looking at maximum wind speed, we see again this 25% increase in risk. This was the change in risk that I called subtle. And I would say that is a pretty subtle change in risk. You'd have to watch the weather for quite a long time to see a 25% increase in risk of a relatively unlikely event. What this means is, what was a 10-year event is now happening every 7 or 8 years. But you don't get a 10-year event, you can't set your watch by the 10-year event. It's just something, there's a 1 in 10 probability of it happening every year. But that means if that switches to there being a 1 in 7 probability of it happening every year, you probably have to wait for a century or so before you even noticed. So these relatively subtle changes in risk are actually the main drivers of change in the main way in which climate change is affecting us. But they take quite a lot of teasing out. You can't just go and look at the weather outside and say that's climate change. We've got to actually interpret it quite carefully with this combination of observations and simulation. So why the numbers matter? Well, here's the first reason. Science is evolving that allows us to quantify the role of human influence in extreme weather, and we can get lots of different numbers out for different weather events. So for example, heat waves in summer, we can see a very strong role of human influence, increasing the risk of heat waves by a factor of 6, meaning a 500% increase in risk, for example. Winter floods, much more subtle increase in risk. And why does that matter? Well, one of the practical reasons is that certainly in the UK, insurers are using the threat of climate change as a reason, whether it's just an excuse or whatever, to actually pull out of a lot of insurance markets. They're saying, we can't insure here anymore because of climate change. Well, if you do the science and work out that climate change is only affecting the risk by 10 or 20%, then that's no reason not to offer insurance. Maybe the insurance should be a little bit more expensive, but there's no reason for insurance not to be offered at all. So that's one area where this work can be really useful, is in providing the risk industry with evidence that, yes, although risks are changing, we can quantify those changes and they can carry on engaging with vulnerable parts of the economy. The other side is perhaps the more controversial one, which of course is this is a quote actually from a very old paper now, but quite a prescient one. David Grossman in 2003 pointed out, he was talking about climate change here. A plaintiff must show that in certain legal jurisdictions, Anglo-Saxon legal jurisdictions at least, that if they've been affected by something, they need to show that whatever it was that was affecting them has increased the risk of the harm that they experienced by at least a factor of 2, and then they'd have a case against whoever was responsible for changing that risk. So it means that for winter storms we probably don't cross that threshold. For heat waves we probably do. So you kind of have to you have to do the numbers in order to know whether or not there is a sense in which responsibility responsibility can be applied here to the consequences of these weather events. Here is, of course, I focused on UK and Irish weather, but there's many other events around the world which have been attributed to human influence. The Syrian drought, again, made somewhat more likely by human influence. 2016 Louisiana floods. And we're now, the science is maturing, that we're now performing a regular assessment. Every year, the Bulletin of the American Meteorological Society issues a special edition which looks at the extreme events of the previous year and asks what was the role of climate change in these various events. I think this regularity is crucial because it means that you don't just look at the events that are likely to go one way. We've got to look at both. We've got to look at boring seasons as well as exciting ones. Otherwise, there's a dangerous sort of filtering process that you only study events where you think you're going to get a particular answer. So one of the points I argue is actually, I think, in the end, and I would say within a decade or so, if it's possible that this may just become part of the remit of Met Éireann, to tell you at the end of a season, yeah, this is the season we've had, and this is what was driving it. This is what the role of various factors was in the weather events that happened over the past season. And if it was part of their remit, that this was just part of their job to do this, it would to some extent, I hope at least, depoliticize the issue a bit. Because if you had a season where the weather was kind of boring and nothing much happened and climate change had nothing much to do with it, that's fine. That would be the result. It would mean that you don't just talk about climate change only when the weather gets exciting. So, and that would be an important message for people to get, is that climate change is there, but it's sometimes, it's affecting some weather events, making some of them more likely, and indeed some of them less likely to occur. Here's an example. The 2015-16 cold winter in the US, which was assessed in this recent BAMS Bulletin of the American Meteorological Association special issue, and in the green line here is probably a good point to focus on. This was the cold winter that occurred in the North Atlantic sector, that green sector here, in 2014. You can see that it was cold compared to recent winters since 1980 or so. But if you try and fit a trend to the 20-year return cold value in that data, it's actually going up. So the risk of such a cold winter had actually gone down due to the trend. It still happened. You know, you can roll a loaded dice and still get a 1, but the probability of it had gone slightly down. So the conclusion of this study, led by Laurie Trernay, was that climate change was not a major factor. And if anything, climate change had made the very cold winter they got in 2015 less likely to occur. So we need to do this work to distinguish between different the weather events to be made more likely and the weather events made less likely. Another important part of the story is that, you know, the meteorological drivers are only part of the story. One of the events that we're going to be looking at in the context of this project is the fodder crisis of 2013, which had a huge impact on the Irish economy. I learnt today actually as big an impact on the Irish economy as the Cork floods in 2009. But this was a crisis that developed over a long period of time. So this is a case where the rolling dice analogy rather starts to break down. When you roll a dice, once you've let it go, it's off. It's gonna fall as it's gonna fall. But this is an event that evolved over a year or more, and perhaps with tighter monitoring of fodder stocks, perhaps the worst impacts could have been mitigated. So this is, you know, you've got to, just because climate change is affecting events doesn't mean there isn't anything we can do about them. And that's got to be a big part of this story, is not only understanding how climate change is affecting individual events, but understanding what that then tells us about how we need to manage for such events in the future. So where's all this going? There's a sense in which if human influence on climate has doubled the risk of an event, then it's to blame for a certain fraction of the losses that have occurred because of that event. And this is, people are getting this, And the reason I think you can be sure that governments in the world are getting this is in the famous Paris Agreement on climate change. Everybody's heard of the 1.5 degree aspiration, and it was a much celebrated agreement. Perhaps people are less familiar with Article 52 of the decisions associated. This is the small print part of the agreement. And in the small print, it was said very at the insistence of certain large countries that Article 8 of the agreement, which is the article on loss and damage, on the kind of impacts I've been talking about, does not involve or provide a basis for any liability or compensation. This is a remarkably clear sentence to appear in a UN document. Above and below it, there's lots of gobbledygook about stuff you really can't even work out what's going on. And suddenly, like a flashing light, this article says, by the way, there's no liability or compensation. It's like, yeah, and I'm not beating my wife. It's like, why do you suddenly feel the need to say this? So there we are. It's in there. It's been said, and this is where it sort of, okay, so this is where I leave my scientific brief, and I should probably immediately say what I'm about to say is, of course, nothing to do with Climate Collab or the EPA. This sentence was inserted into the decisions associated with the Paris Agreement at the insistence of, among others, the United States of America. Not, of course, the present government of the United States of America, but the previous administration, because they knew perfectly well what would happen if they didn't have this in there. So it's in there. Parties to the Paris Agreement have got this disclaimer in. It's agreed. All countries have signed up to say they're not going to start insisting on liability for climate change or for adverse weather events made more likely by climate change under the Paris Agreement. So what would happen then if a major exporting nation were to withdraw from the Paris Agreement? Until recently, this would have seemed a completely fanciful possibility, but actually we now have the very real possibility that the United States might actually pull out. What would that mean? Well, this article wouldn't apply anymore, would it? And it raises the possibility that we need something to identify goods and services supplied by companies that work and source their raw materials from regions that support the Paris Climate Agreement, so that we know which the other ones are. At the moment, there's no downside, really, to pulling out of the Paris Agreement. But if we all knew where goods and services were coming from, then that might give certain companies pause and might encourage them to encourage their government not to pull out of global agreements to do something about climate change, for fear that the bills might start to come home to roost when the bills come. Well, you know what I mean. As the impacts of climate change become clearer, I think that's probably quite a good point to move to questions, in the hope that I sort of thrown in enough controversy at the end there to get some questions going. Thank you.